When we talk about our neurotransmitters, again, I mentioned this when we talked about the muscle system. We could spend weeks and weeks and weeks on all of the different subtleties among neurotransmitters. There's lots and lots of different types. They have very specific jobs. Some of them only affect one effector organ. All right, so we could spend a good amount of time discussing neurotransmitters. But what we're going to do before we can even begin talking about neurotransmitters is figure out what do we mean by a neurotransmitter. Well, in order for a chemical, any chemical, to be considered a neurotransmitter, it has to meet these three criteria. It has to check all three of those boxes. These boxes we're going to talk about in a second. You can't just say, well, that's 2 out of 3, it hit 1. No, in order for a chemical to be considered a neurotransmitter in your body, it has to meet all 3 of these criteria. Check all 3 of these boxes. First, it has to be present in the presynaptic terminal. It has to be in the knob bit of the neuron, which makes sense. If it's not there, if it's not inside of the neuron, if it's not in that presynaptic terminal, how is it going to be able to do its job, which is going to be to swim across the synaptic cleft and to affect somehow the membrane of the effector organ? Number 2, it has to produce ion fluxes when applied to the postsynaptic membrane. Flux sounds like a fancy word, doesn't it? What the heck does it mean? A flux is a fluctuation, a change, a movement. So in order for a chemical to be a neurotransmitter, it has to cause ions to move when applied to the postsynaptic membrane. Let's think about acetylcholine for a second. When we applied acetylcholine to the skeletal muscle cell, what happened? The calcium ion channels opened and allowed an ion flux, allowed the calcium to move from inside of the sarcoplasmic reticulum to outside. When we think about a neuron, right, we apply that neurotransmitter, it's going to open those sodium ion channels and cause sodium to move from outside to in. Right, so we have to, whatever this neurotransmitter is, whatever this chemical is, when it's applied to a postsynaptic membrane, it has to allow some kind of ion movement. And number 3, there has to be a natural way of removing it from the synaptic cleft. There's got to be a way to get it out of there. We had our acetylcholine esterase, you'll remember, from our skeletal muscle, where it was located in our synaptic cleft. It just lived there, right? It just hangs out there so that when acetylcholine comes across, it can break it in half and cause it to be inactive. So there might be an enzyme. Acetylcholine esterase is a great example of that. It may also simply be pumped whole. The chemical doesn't change, but the neuron, the presynaptic terminal, has a way to pump that back in. It actively transports that neurotransmitter back into the neuron to put it into a synaptic vesicle so we can start the process all over again. Now, let's look at the functional classification of neurotransmitters. If you look in your textbook, there's a table or a chart, if you will, a full page, if not 2 pages, talking about really specific concepts behind these. I'm using a broad brush because, as I said, we could spend almost a semester on neurotransmitters. Our first functional classification, and again, functional classification is how they do their job. The first functional classification is excitatory and inhibitory neurotransmitters. Now, the name in itself should be really clear for you to understand what these neurotransmitters are going to do. Some neurotransmitters cause something to happen. They would be excitatory neurotransmitters, while others inhibit something from happening, cause it not to happen, where those would be inhibitory neurotransmitters. Here's where it gets a little dicey. Some can do either, depending on what the postsynaptic membrane is that they're going to bind to. Hopefully that makes you go, huh? What? Because it is. It's a little bit weird. What we're saying here is we have a group of neurotransmitters that when applied to a postsynaptic membrane causes something to happen, a contraction. Okay, we have another group, those are excitatory. We have another group of neurotransmitters that when we apply it to a postsynaptic membrane, it causes something to not happen, to stop happening, maybe a glandular secretion. Now, here's the rub. Sometimes we have neurotransmitters that can do either depending on what they're going to be applied to. They can be excitatory or they can be inhibitory. For example, ACH, hopefully you remember ACH is our good old friend acetylcholine. Well, when acetylcholine is applied to, reaches the receptor molecules of skeletal muscle, it's excitatory. It causes a contraction to happen. When we apply acetylcholine to cardiac muscle, it is inhibitory. Now you got to think about this for a second. We're not saying that it doesn't allow cardiac muscle to contract because then you'd be dead, but it might slow it. Okay? It's going to cause those contractions not to happen quite as quickly as they may. Our other classification, functional classification, is ionotropic and metabotropic. Right? Hopefully when you look at metabotropic, hopefully when you look at both of these words, you see another word in it that's going to help you, hopefully. Okay? When I look at ionotropic, I see ion. When I look at metabotropic, I see a good chunk of the word, a part of metabolism. That's going to be your difference, right? So focus on that. Ionotropic neurotransmitters are also referred to as direct action neurotransmitters. Very simple. You apply them, they cause something to happen. If then, okay, if I apply an ionotropic neurotransmitter, then something will happen. In this instance, they're going to open ion channels, which was going to allow ions to move. It's going to cause that ion flux that we talked about. This will cause a very rapid response in a postsynaptic cell. A good example of this is one that we've used for a few weeks now, acetylcholine. When acetylcholine docks into a receptor molecule of a skeletal muscle, there's not downtime, there's not a delay. As soon as it docks into it, connects to your receptor molecule, it changes the sarcolemma, goes down the T-tubule, opening up the calcium ion channels in the sarcoplasmic reticulum. It's instantaneous, direct action. Okay? The neurotransmitter causes this to happen. It causes an ion shift. We can compare this with metabotropic or indirect action. These neurotransmitters promote longer lasting effects. Think back to when you were in maybe 6th or 7th grade, okay, and you liked a girl or a boy in your class. Okay, direct action would be you go right up to that girl or boy and say, I think you're cute, you're dreamy. But that's not what we do in 6th or 7th grade. That's not what we do as adults, really, even. But nonetheless, we'll go with 6th or 7th grade. We ask our friend to go ask Billy if he likes us. God forbid we go right up to that person and say, hey, I think you're kind of cool. What do you think? No. We're going to send somebody in between. Okay? That is an indirect action. That's what this type of neurotransmitter is going to do. They act as an intracellular second messenger molecule. What we're saying, the neurotransmitter is the friend that you're asking to go ask that person you think is dreaming. Okay? Direct action, I go up, I ask that person. Indirect action, I ask a friend to ask a friend. That's what we mean by an intracellular second messenger molecule. An example of this type of neurotransmitter are endorphins, right? And these are those kind of pleasure molecules that we talk about, right? When you exercise enough, you get an endorphin rush. I'm still waiting for mine, but nonetheless, right? We'll end here for this lecture, and we'll start up next time with looking at the specific types of organs